Today I'm going to talk to you about a subject near and dear to my heart, perpendicular bisectors and angle bisectors. Both of them are very useful in many contexts, and what's useful about them comes not just from their definition but also from the perpendicular bisector theorem and its converse and the angle bisector theorem and its converse. So let's look at first what a perpendicular bisector is. Key thing is that there are two words in perpendicular bisector. There's perpendicular and there's bisector. That's key because those are the two characteristics you have to have. Perpendicular. For something to be the perpendicular bisector of a segment, it has to be perpendicular to the segment. Okay, and I'm freehanding this, so forgive it if it's not exactly perfect. Okay, so it has to be a right angle. The other part is that it has to bisect the segment. Bisect and intersect, sometimes people get mixed up. Intersect just means touch. They have a point in common. Bisect is much more precise than that. Bisect is much more specific. It says not only do they touch in such a way that it is equidistant from either end of the segment when it crosses that segment. In other words, it goes through the midpoint. In other words, these two sides are congruent. As a matter of fact, we might as well call that M for midpoint. All right, so from A to M is congruent to from B to M because this line of mine, and I'm going to call it line, why not L? That's a script L. We sometimes use script lowercase letters for a line. And that line L is the perpendicular bisector of segment AB. Now, what the perpendicular bisector theorem says is that the perpendicular bisector, every single point on the perpendicular bisector of a segment is equidistant from the endpoints of the segment. Every single point on line L is an equal distance from A and from B. So it doesn't matter whether I choose this point, or this point, or this point, or this point, or this point. They're all an equal distance from A and B. Let's prove it. I'm going to take this point, and let me call it point C. I'm going to attach it to A, and I'm going to attach it to B. What have I just created? Two triangles. These two triangles are congruent. How do I know they're congruent? Think about it for a second. Side angle side. This is a right angle, so this is a right angle. Those two angles have to be congruent by the right angle congruence theorem. It says all right angles are congruent. This segment AM is congruent to segment BM. So that's a pair of congruent sides. Then we have this shared segment, the shared side right down the middle. CM is congruent to itself by reflexive property. And thus we have side angle side. Remember that just because it's a right triangle does not make it hypotenuse leg. We don't already know anything about the hypotenuse here. As a matter of fact, that's where we're trying to go with this. We're trying to prove that every point, including point C, on the perpendicular bisector would be equidistant from A and from B, the endpoints of the segment I'm bisecting. So knowing that these two triangles are congruent, then I can say by CBCTC that these two segments are congruent. And if CA is congruent to CB, then I've just proven what I set out to prove. That for any point C, because I could have put C anywhere, and all of this stuff still would have worked, any point C, any point that's on the perpendicular line, the perpendicular bisector of segment AB is going to be equidistant from points A and B, the endpoints of the segment. Now the converse of that is also true. Meaning, if I have a segment, let's call this segment MN. And then I have a point, and I'm going to call it point T. if I know that point T is the same distance from M that it is from N, meaning if I know that MT is the same length as NT, then that automatically tells me that T must be on the perpendicular bisector of segment MN. So that means this line, the perpendicular bisector of segment MN, must have T on it. Okay, so that's the opposite. The first way, the perpendicular bisector theorem says every point, if a point is on the perpendicular bisector, then we know it's equidistant from the endpoints of the segment. What we just did here said, we know this point is equidistant from the endpoints of the segment. What does that mean? It means it must be on the perpendicular bisector. That's the converse. Let's use that a couple times here. Let's say we have my drawings were looking too pretty. I had to start making them look ugly, sorry. This figure and we're going to start out, given that line L, this is one of the check it out, try me kind of problems from your book. Given that line L is the perpendicular bisector of DE, segment DE, and that EG is equal to 14.6, find DG. Okay, so if I know that EG is equal to 14.6, find DG, well, it's going to be exactly the same. Ta-da! All done. Notice that I can find other things here if I wanted to. Let's say that I knew that this was from E to G was 13 and from F to D was 5. And I'm asked to find FG. Few things to look at there. First of all, if you're asked to find, and it has the name of a segment and there's nothing over the top, that means the length of FG, whether you're asked to find it or anything. Anytime you see the name of a segment and there's nothing on top of it, that means the length of that segment. Or you could call it the distance between F and G, same idea. So I'm supposed to be finding the distance between F and G. Think about how you do that. Well, if this truly is the perpendicular bisector, if we have been given the information that L is the perpendicular bisector of DE, then if this is 5, this is 5. And if this is 13, this is 13. And these are right triangles. So I can take one of them and use the Pythagorean theorem and say, let's call this x. 5 squared plus x squared equals 13 squared. Remember to set it up. A squared plus b squared equals c squared. A and b are always the legs. I actually like to say leg squared plus leg squared equals hypotenuse squared instead of a, b, and c. Because sometimes people forget that it's the hypotenuse that has to be the one by itself over here. And subtract 5 squared from both sides. So I have x squared equals 169 minus 25. 169 minus 25 is 144. Take the square root of both sides, and I get plus or minus 12, but this context, it could only be a positive 12. So this is 12. So the length of FG is 12. Let's get rid of all that and call it 12. All right, so that's perpendicular bisectors. Now, let's look at angle bisectors. Angle bisectors, as you might imagine, bisect an angle. All right, so an angle bisector, it doesn't have to have two things like a perpendicular bisector, it just does one thing. It cuts that angle into two congruent smaller angles. So, there you go. This line L is now an angle bisector of angle ABC. Excuse me. All right, the angle bisector theorem, we have an angle bisector theorem as well. It's very similar to the perpendicular bisector theorem. The angle bisector theorem says that every single point on the angle bisector, every single point on this line, is the same distance from this side of the angle, meaning this ray, as it is from this side of the angle, meaning this ray. Okay, any point here is the same distance from here as it is from here. Now let me just point out to you one little thing that you may or may not remember, and that is if we want to know the distance from a point to a line or from a point to a straight object, it will always be the length of the perpendicular segment. Meaning, I wouldn't measure from here to here and say, well, that's the distance between that point and that line over here. No, the closest distance is what I mean. And so you go to where it makes a right angle. Okay? It's kind of like if I'm standing here, I run my measuring tape up to the wall at such a place that it would make a right angle with the wall. That's going to be the shortest distance between my point and my line. So the shortest distance, or the distance from a point to a straight object, is always the length of the perpendicular segment. So that means if I'm talking about distance from a point to a line, I show that's what I'm talking about by showing that it's a perpendicular segment. So right here, to show that I'm talking about the distance from this point to this ray, you could think of it as a line because it's part of one. I put a little right angle to show this is the distance. Okay, same thing over here. Get it back up. There we go. And that way you know that I'm talking about these distances. This is the distance from this point to this line, distance from this point to this line. These two would be congruent. That's what the angle bisector theorem says. Of course, the angle bisector theorem converse says it backwards. Says, if you know that a point, a randomly existing point, in the interior of an angle, like say my little friend here, point M, is equidistant from the two sides of the angle, then it must lie on the, you guessed it, angle bisector of the angle. And that's what the angle bisector theorem converse says. So again, let's go ahead and do the little you try it problems from your textbook. And we have a picture that looks a little bit like this. Fairly little, so don't get too upset if you see it yourself. Here is point X, point W, point Z, and point Y. Okay, so it says given that ray YW bisects angle XYZ and WZ is 3.05. Find WX. Well, that would also be 3.05. Ta-da! Again, remember these are right triangles, so I could do things with that with Pythagorean theorem. The next one says given that angle WYZ is 63 degrees. That's right here. XW is 5.7. And ZW is 5.7. Well, you didn't really have to give that. Well, sort of. Maybe so. Find the measure of XYZ. Okay, yes. This one did not start out telling me that this was an angle bisector. It just told me this is all stuff here right in this picture. And here's one angle, and look, these two things happen to be the same. So in other words, they're wanting me to conclude that YZ must be the angle bisector. In other words, I can say, oh, since this point W is equidistant from the two sides of the angle, then it must lie on the angle bisector of the angle, which means YW is the angle bisector, and this is also 63 degrees. Okay? Now, this is where things get a little bit more interesting. We are asked to write an equation, and it says in point slope form. We'll do it in whatever form we feel like writing it in. For the perpendicular bisector of the segment with endpoints, and so I'm going to call it just the name, the endpoints, of PQ, where P is 5, 2, and Q is 1, negative 4. Okay, so sorry it's off the side there. P is 5, 2, somewhere like this. Q is 1, negative 4, so someplace like this. And I'm supposed to be writing an equation for the perpendicular bisector. Well, the perpendicular bisector of this segment is going to be a line. It's going to be a line that comes through somewhere like this. Remember, this is sort of a freehand sketch, so not necessarily the most accurate thing. So here are the things I need to know. I need to know where does it touch segment PQ, and I need to know what's its slope going to be. If it's perpendicular, then these two should have opposite reciprocal slopes. If it's a bisector, it needs to go right through the midpoint. So those are the two facts I'm going to use to help me find this equation. That if my dotted line here, the equation I'm trying to look for, says write an equation for the perpendicular bisector. So I'm trying to find the perpendicular bisector. If it's a perpendicular bisector, it's perpendicular, which means its slope is the opposite reciprocal of whatever the slope of PQ is. And bisector means it goes right through the midpoint. So first thing I'm going to do is I'm going to find the midpoint of PQ. Midpoint of PQ. Midpoint formula, please remember, is nothing more than averaging the x's and averaging the y's. Averaging the x's means add them together and divide by 2. Averaging the y's means add them together and divide by 2. There's your midpoint formula. So average the x's. 5 plus 1 is 6 divided by 2. Average the y's. 2 minus 4 is negative 2 divided by 2. And we get 3, negative 1. So that's where this point, where this perpendicular bisector intersects the segment PQ. The next thing I need to know about it is its slope. Okay, so I'm going to find the slope of PQ. Slope of PQ, remember the slope formula is the change in y over the change in x. That's what the slope formula says. Change in y over change in x. We use the Greek letter delta to stand for the change in. Okay, so I'm going to subtract my y's. 2 minus a negative 4 is 6. 5 minus 1 is 4. So the slope of PQ is 3/2. That means the slope of my line needs to be negative 2/3 because perpendicular lines have opposite reciprocal slopes. Another way of thinking about that, remember, these two numbers, 3/2 and negative 2/3, they're opposite reciprocals. Remember that another test for opposite reciprocals or slopes of perpendicular lines have a product of negative 1. If you multiply them, you get negative 1 every time. Okay, so now I know the two things I need to know to write this line. Excuse me, write the equation of the line. I have a point and I have the slope. So let's go ahead and use point slope form. Here's point slope form. My point is 3, negative 1. So I'm going to plug in the 3 here and the negative 1 here. My slope is negative 2/3, so negative 2/3 goes right here. So I have y minus a negative 1 equals negative 2/3 times the quantity x minus 3. If I wanted to do it in slope-intercept form, I can easily put it there now. I'm going to distribute this. Y plus 1 equals negative 2/3 x plus 2. Negative 2/3 times negative 3 is positive 2. Subtract 1 from both sides, and I get y equals negative 2/3 x minus 1. So you could have it in this form, point slope form, or slope intercept form. We could put it in standard form. Let's do that, just to remember what standard form is. Standard form, the x comes first and then the y. So let me add this to both sides. It's not very often that you're asked for standard form, but what the heck. All right, this is not in standard form yet. Standard form, I want integers in front of my variables, and I don't want my leading coefficient to be negative. Remember, there's a trick when you have a fraction in your equation and you want to get rid of it. You multiply the whole equation, every single term, by the denominator. If you have multiple fractions, you find a number that all the denominators go into and do it that way. So this time I'm going to multiply the 3, and I get 2x plus 3y equals negative 3. And that's the standard form equation for my line. And there you have it. Okay, so go ahead and try your homework. Not try it. Do it. There is no try, only do. And succeed at it. I'm not going to put your homework on here because who knows, I might want to use this video next year and change the homework. So I will go ahead and let you know what the homework is on eClass. Have a good evening.